Okay, so the last proof technique that we're going to talk about here is proof by induction. So this is basically if we have an ordered set, a well-ordered set, then we can prove well-ordered just means that there's a discrete next element, or that the technical term is for every subset there is a least element. But in practice, it just means that there is a discrete next element. We can prove for a base case n, or base case n, and that if base case, and if it works for the nth element, it works for all, then it works for the n plus 1 element. And our statement holds. For n greater than or equal to our base case. So sometimes we'll have things that start at 1 or 2 or 0, or they don't have to start at our first number, but once we prove for our base case, and then we prove what's called our inductive step, then we show that it works for everything up to infinity, or that it works for all of the subsequent steps. So we're kind of, let's see, let's mess things up. Cool, no. So you can picture this basically as a ladder, and we can say that if we can get in at our base case, that puts us on the ladder, and then the second step, our inductive hypothesis, allows us to jump from one rung to the next rung to the next rung. So that's the concept of induction or weak induction. If it's not specified, we'll be using weak induction. So the sum of, so we wish to show that the sum from I equals 1 to n is of I is equal to n times n plus 1 over 2. And we showed this earlier by cases, but we're going to show it by induction now. So first, our base case, let n equal 1. In this case, we get the sum of I equals 1 to n of I is just equal to 1, and that happens to be equal to 1 times 2 over 2. I'm doing a recording right now. So that is equal to, so that checks out. That's n times n plus 1 over 2. So our base case works. Now we want to show our inductive hypothesis. So assume that the sum of I equals 1 to n I is equal to n times n plus 1 over 2, and we want to show that that implies that the sum of I equals 1 is going to be equal to n plus 1 times n plus 2 all over 2. Cool. So what is this guy? So this guy right here, that's the same thing as plus n plus 1. We're just taking this up here, and we're adding the one extra element. So that's equal to n times n plus 1 over 2 plus n plus 1. And now I'm just going to want to put them on the same base. So in order to do that, I'm going to rewrite this as n times n plus 1. Actually, I'm going to distribute. So I'm going to do n squared plus n over 2 plus 2 times n plus 1 over 2. So that's equal to n squared plus 3n plus 2 all over 2. And then I can factor this guy out, and that's equal to n plus 1 times n plus 2 all over 2. So therefore, our inductive hypothesis holds, our base case, and inductive hypothesis hold. And for n greater than or equal to 1, we could actually have done this for 0, but we did it for 1. For n greater than or equal to 1, the sum of I from I equals 1 to n is equal to n times n plus 1 over 2. So going back to this ladder analogy, the base case right here is we showed that we can get on at n equals 1, and then the inductive hypothesis showed us how to jump from one rung to the next rung. So we show that if we are on the nth rung, we can go to the n plus 1th rung. So this actually might be one of your homework problems, but we want to show inductively that the sum of odd numbers, or that every square can be written as a sum of odd numbers of the first. So k squared is equal to the sum of 2k plus 1 from, let's do I equals 1 to k. Oh, sorry, 0 to k minus 1. This might look a little bit weird, but basically I just want the first odd number is going to be 1, so I need to look like this. So base case, this is k is an integer greater than 0, so k is a positive integer. The base case right here is going to be k is equal to 1. In this case, we get k squared is equal to 1 is equal to the sum I equals 0 to k minus 1 would be 0, so 1 minus 1 is 0, of 2k plus 1, just 1. So base case holds. Typically, your base case is going to be very easy. Now, the inductive hypothesis, assume that k squared is equal to the sum I equals 0 to k minus 1 of 2i plus 1. And we wish to show that k plus 1 squared is equal to the sum up to k equals 0 of 2i plus 1. Now, how are we going to do this? Well, we're going to look at this guy. We're going to distribute them. We're going to do it. That is k plus 1. Squared is equal to k squared plus 2k plus 1. So k squared right here, because we already know what that is, that's this guy. So that's equal to I equals 1, or I equals 0 to k minus 1 of 2I plus 1. And then this guy is going to be plus 2k plus 1. But this guy is of the same form as this guy. Therefore, we can actually write this as the sum up to k. This is just the next one in the next one in this index if we were add the k element. I equals 0 of 2I plus 1. Therefore, our base case and inductive hypothesis hold. And therefore k squared is going to be equal to the sum of I equals 0 to k minus 1 of 2k, or 2I plus 1 for all k and z greater than 0. Cool.